In the last video, we talked about the problem number 46. We talked about, oh, come on, computer, here we go. We talked about problem number 46 from section 14.2, and we were trying to find the volume of this region that's sketched here between two planes, but inside of the cylinder. And the cylinder established our domain D in the xy plane as a circle. And so we had set this problem up in Cartesian coordinates, and that just means xy or rectangular variables. Okay, so we know that x and y is down here in the xy plane, and we know that x and y, if we move in the xy plane, we're moving along a square grid. Okay, that's why those are Cartesian or rectangular coordinates, x and y coordinates. So I'm going to assume that you have come to class and we have talked about the transformation, the polar coordinates transformation, t of r theta as r cosine of theta, r sine of theta. Okay, I will assume we've talked about this transformation. It's a transformation that takes two variables and gives you two new variables. Okay, so this transformation takes as input two variables, r and theta, and returns two new variables. X is the first entry, and that function is r cosine theta, and the y entry of our vector is r sine of theta. So this is an example of a vector valued function. Example of a vector valued function in two variables. And our two variables are r and theta. You should contrast this with our parametric curves, which were a function like r of t was like 1 cosine of t to sine of t. This was a vector valued function, 2D vector valued function in one variable. The transformation we were talking about here is a 2D vector valued function in two variables. And so in class we most definitely would have talked about this transformation, and we would have talked about the Jacobian of that transformation, and we would have talked about the determinant of that Jacobian. And when you take the determinant of the Jacobian of this transformation, you get the variable r. The Jacobian here, if you wish to know, is take the first entry and take its gradient. So this is the gradient of t1, and then take the gradient of the second entry and stack them on top of each other. This is t1, the function t1. This is the function t2. Take their gradient, so take the partial with respect to, take t1, take the partial with respect to r, take the t1, take the partial with respect to theta, take t2, take the partial with respect to r, and take the second function t2, take the partial with respect to theta, and you have a matrix. So we would have talked at this point about then changing the double integral, doing a change of coordinates. This is the kind of the equivalent of u substitution. The square root of 4 minus x squared was our original integral up to y is equal to the square root of 4 minus x squared. And then x goes from -2 to x is equal to 2. And we are integrating the function 4 minus y dy dx, I'm sorry. So the goal is to change variables we want to change variables to r and theta. Okay? So part of this is pretty simple. Wherever you see the x, you need to substitute r cosine theta, and wherever you see the y in the function, you need to substitute r sine theta. So that is pretty straightforward. We get r sine of theta. And we need to change our dy dx into dr and d theta. But you can't just do that without some sort of compensation, as we've discussed in class. The compensation is to put the determinant of the Jacobian there. Okay, and that would be the variable r. And now we need to describe the region in terms of r's and thetas. So r is our first integral, and theta would be our second integral. Okay. So we would have spent time in class talking about how to describe this region in the xy plane. This was our domain D. Trying to describe that in terms of variables r and theta. R is the radius variable. So to describe this region, we would like to view it just as a bunch of concentric circles of varying radii, and the radii will change until it goes from 0 until we get to the radius of 2. And theta is the angle variable, and the angular description of this whole region is that if the radius goes from 0 to 2, we need to do full circles. We need to go all the way around, so theta will go from 0 to 2 pi. And my claim is that if we can do this integral, we will have the same answer as if we had done this integral. We've just transformed it into new variables. So this integral is much easier to do. We're doing an r integral first. Let's just do this as an iterated integral. Focus on this term first. So if you go from 0 to 2, 4r minus r squared sine of theta. And we're going to do this as an dr. We're going to do this as an r integral, so theta is a constant. And when you integrate this, you should get 4r squared divided by 2 minus r cubed over 3 sine of theta. And then evaluate from 0 for r to up to 2. Which gives you 2 squared is 4, 16 divided by 2 is 8. R cubed is 8. R cubed is 8, and then we get sine of theta. That is the top limit, and you get 0 for the bottom limit. So let's move on now to the second integral from 0 to 2 pi of the function of theta that we found from the first piece, minus 8/3 sine of theta, d theta. And these are really easy integrals to do. You're going to get 8 theta minus 8/3. What has a derivative of sine? That would be a negative cosine of theta. And then we need to evaluate from 0 to 2 pi. So what do we get here? You get 16 pi plus 8/3 cosine of 2 pi minus 0 in for theta gives you 0 plus 8/3 cosine of 0. Cosine of 0 is equal to 1. Cosine of 2 pi is equal to 1. So this reduces to 16 pi. And we'll get plus 8/3 plus 8/3. minus 8/3. The 8/3 cancel and you're left with 16 pi, which was the answer we had by doing the problem in Cartesian coordinates. So this is using polar coordinates to do a change of variables, and you can either do the integral in Cartesian coordinates or the integral in polar coordinates. I think I will let you compare to see which one you felt was more straightforward, and I think you will find that polar coordinates wins, in my opinion. And that's the end of this video.